In this example problem, we're going to find a process variable, specifically the heat that is enters or exits a gas as it goes through a process, and the process is going to be described on a PV diagram. Now, um, this is not the most obvious thing on a PV diagram. The easiest thing to see is the work on a PV diagram, because the work is basically just the integral, or area under the curve, with the additional minus sign to mean that if it expands in volume, then you lose work. You can, however, get the heat with some additional information by applying the first law of thermodynamics, which says that the change in internal energy is equal to the heat Q plus the work W. So if we want to find the heat, what we need to do is find the internal energy change and subtract out the work. So now what we have is two steps. Step 1, find the work. Step 2, find the change in the internal energy. Step 3, let's combine them together. So let's go through that. First, let's find the work. Now, the easiest way to do this, if I had a function, it's not too hard to write this as a linear function. You could integrate it up and just add a negative sign and find the work. Or we can just kind of use a little bit of algebra and know that, hey, I have two regions here, region 1, region 2. This is a triangle, so if I want to find the area of that, if I call this delta P, just the magnitude of that delta P, so that'll be 30,000 pascals. And I call this difference right here delta V. Again, just meaning the magnitude, which would be 0.4 cubic meters. Then this part of the area would be 1/2 delta P delta V, width times height. And then this area is just going to be the lowest pressure. I'll call that P1. Is equals to P1 times delta V. That's the height times the width. So the total work is going to be, I have to add a negative sign in here, 1/2 delta P delta V plus P1 delta V. Okay, so that's the work, and then I have the values on it, so I could plug it in. I'll hold off until I do this all. So that'll complete a first step, finding the work. The second step is to find the change in the internal energy. The way we're going to find the change in internal energy is looking at the change in this change in temperature. So if you know the change in temperature, you can find the change in internal energy by using a specific heat at a constant volume. Now note, this is not the actual process, meaning that it's not actually at a constant volume. So why do we use the constant volume condition? Because that looks at just the part of the energy, the heat that is put into it, that goes into internal energy. So this looks at just the component of basically heat might be going in, and it'll split between work going out and internal energy going into internal energy. And this is just going to look at the amount that goes into internal energy. So what do we know? N is the number of moles, which is 2 moles. So N is 2. The change in temperature is the other part we're going to have to get at. We'll have to calculate the temperature using the ideal gas law, PV equals nRT, because we're talking about an ideal gas. So if we know N, which is 2, and the pressure and the volume at either time, so I'm going to call this point 2 and this point 1, then I can find the temperature at these times. So if I just solve for T, it's PV over nR. So the initial temperature is equal to P2 V2 over nR, with the pressure and the volume up here. The final temperature is down here. That's P1 V1 over NR. And now I need to know the specific heat capacity at a constant volume. And that's where the monatomic part comes in. So the monatomic gas means that it only has 3 degrees of freedom. And these are all translational degrees of freedom. They don't freeze out. So when doing the mode counting, we only have 3 modes. And you take that 3 and you multiply by 1/2 R to get the specific heat capacity. Okay, so now we have all the parts. Let's simplify our change in internal energy. So we have N times 3/2 R times P. So the final is P1 V1 over NR minus the initial P2 V2 over NR. The NR part can cancel out, so I just get 3/2 P1 V1 minus P2 V2, and I just have to go through and plug in. So Q equals the change in internal energy, which is 3/2 P1 V1 minus P2 V2, and then I'm going to subtract out this amount right here. Note then the negative sign is going to cancel, leading to a positive, minus a negative. 1/2 delta P delta V plus P1 delta V. Now, I'm kind of out of room right here, so I'm going to continue down over here to give myself plenty of room. So Q is equal to 3/2. The first pressure is P1 is equal to 70,000 pascals times V1, which is 0.5 cubic meters, minus the other pressure, 100,000 pascals times the other pressure. That part is the change in internal energy. Let's add the work part here. That's 1/2. The change in pressure was, as we noted, 30,000 pascals. The change in volume was 0.4 cubic meters. And then we have the area on the bottom, the P1, which is 70,000 pascals, times the change in volume, which is 0.4 meters cubed. And when you multiply this all together, you get 70,500 joules. Or, in other words, 70.5 kilojoules. So you have to have a lot of heat flow in during this process, partly because you're losing energy during this process as work, and also the temperature increases rather dramatically. When you work through the numbers for the initial and final, you end up finding that it starts around 600 Kelvin, quite hot, and it goes to about 2000 Kelvin, which is even hotter. So in order to raise the internal energy while you're losing work, you have to add a lot of heat.